Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of graphing using calculus. We've just finished a single example. It took quite a while, and this one will be no different. We're going to go ahead and just tackle this. You should have watched the first one, so I don't have to repeat all the information that I've stated here. So let's just dive into the example. So here we go. Graph the function h of x equals x times the quantity 6 minus x to the 2/3. This looks similar to the last example. There is a very subtle difference between this one and the previous example. So let's go ahead and see what that subtlety is. Writing out everything we need, everything we learned from algebra 1, our y-intercept. If you let x equal 0, you get 0. So I'll start building my table of values, x versus h of x, and we have 0, 0. And then our x-intercepts. You can easily see just from the function, our function turns into 0 when you plug in x equals 0. It also turns into 0 when you plug in x equals 6. So I'll go ahead and write that second point there, 6, 0. Notice how you start kind of speeding your way through. The domain of this function. Well, looking at the function itself, you can easily see that you're taking the cubed root of something. So that's perfectly allowable. You could take cube roots of negative numbers. So in this case, the domain is all real numbers, which tells us also that we will not have vertical asymptotes, but we'll get to that in a moment. Next thing we're going to look for is symmetry. And so let me go ahead and just in blue ink, look at h of negative x. Maybe we have symmetry, maybe we don't. Let's find out. That'll be negative x times 6 minus a negative x being raised to the 2/3 power. That is the same thing as negative x times 6 plus x to the 2/3 power. Now the question is, can you make this the opposite of the original function, or can you manipulate this somehow? And the answer to that is heck no. There's just no way you can make this be some number times x times 6 minus x to the 2/3. No matter how hard you try, because these signs are not opposite here, you can't get them to be opposite. There's just no way you can do that. So it's locked out. This is neither odd nor even. So I'm just going to put symmetry none because there is no symmetry. So symmetry none. So notice you can go very quickly if you're kind of used to this. Now we'll deal with vertical asymptotes. As I said, domain is all real numbers, so vertical asymptotes don't exist. Horizontal asymptotes might be helpful if something disappears or if this becomes finite as x goes to infinity. I'm just going to go ahead and just tell you right now, as x goes to infinity or negative infinity, this will be an infinite. The function will become infinite. So there are no horizontal asymptotes. You can take that limit if you want, but you should be able to, at this point, just look at this and say that will not become finite and nothing will disappear. Remember, you're looking for oblique asymptotes. You're looking for a term, which there is no term. There's only one term on this, so you won't have an oblique, but you're looking for a term to disappear if you have an oblique, which again, this only has one term, so nothing's going to disappear. And if you have a horizontal asymptote, you're looking for this to be finite, but as x goes to infinity or negative infinity, it doesn't become finite. Therefore, our horizontal asymptotes do not exist, nor do our obliques. So I'll write that in there. So we're done with the algebra that quickly. So compare that to our last example where I took quite some time for that. Let's now go with the derivatives. So h prime of x is equal to, well, if you take a look at that function, it's going to be a product rule yet again. Not our favorite, but such is life. So derivative of the first is 1 times 6 minus x to the 2/3 power plus x times the derivative of 6 minus x to the 2/3, which is 2/3 times 6 minus x to the negative 1/3 times a negative 1 by the chain rule. Cleaning this up, you get 6 minus x to the 2/3 minus 2x over 3 times 6 minus x to the positive 1/3. All of your algebra is assumed here as a prerequisite, so I'm not speeding, but I'm just doing it as quickly as I would expect you would do this. I'm going to multiply numerator and denominator of that first term by 3 times the quantity 6 minus x to the 1/3 power, so I can combine these. And when you do that, you get 3 times 6 minus x to the 3/3 minus 2x all over 3 times 6 minus x to the 1/3 power. And one final little step for simplification. You get a negative 3x minus 2x, so negative 5x plus 18. This, by the way, was an exam problem that I gave the last, I think, couple semesters. This is to give you an idea of what your instructor might expect of you on an exam. All right, so let's talk about when this derivative does not exist. H prime does not exist at, let's see, x equals 6. And H prime is equal to 0 at x equals 18/5. I'm assuming you can solve that stuff there, so I'm not really super concerned about it. We don't have symmetry. The last problem that we did had symmetry, so we only had to graph out half the number line. But in this case, unfortunately, we don't have symmetry, so we have the full number line. 18/5 is 3.6. So I'm going to plot that here, 3.6 and 6. Oops, and I want an open circle where 6 is. Sorry about that. All right, and so let's test values. You could plug in 0 to test that first interval. So our derivative at 0 will be 18 over some positive number. That's all I really care about. So I know my derivative is positive here, or in other words, our curve is increasing. Between 3.6 and 6, I'll plug in 5. If you plug in 5, you get a negative 25 plus 18, or a negative number in the numerator. And 6 minus 5 is positive, so you get negative altogether. So your function's decreasing. And remember, right here, our derivative is non-existent. So we might have a kink, cusp, or corner, or it might go vertical for a moment. And I didn't mention it in the last video. Oh, that sucks. But in the last video, just to let you know, our derivative didn't exist at 2. Where did it not? At 2. So it actually went vertical momentarily. I hate myself for not doing that. But it went vertical momentarily there at 2. That bothers me. It really, really bothers me that I did that. Anyhow, I'll try to remember it this time. Let's see. Pick a number greater than 6, like 7, right? And you'll get negative 35 plus 18, which is negative, over 6 minus 7, which is negative, and you're taking the cube root of that negative, which is negative. So you get negative over negative, which is positive. So you know your function is increasing. This place where the derivative does not exist is, let's see, it goes from decreasing to increasing, so it's a local min. At 3.6, it goes from increasing to decreasing, so that's a local max. I will add those two x values to my table if they're not already there. If you look at the table, 6 is already there, but 3.6 is not. 3.6 actually was 18/5, so I'm going to go ahead and write that in here. 18 over 5. By the way, if I fixed the other video, then there you go, I fixed it. So without you ever knowing until now. All right, 18/5, and I want to evaluate my function at 18/5. The fact that I'm taking a cubed root is a little bit daunting. So if you look at h of 18 over 5, you'll get 18/5 times 6 minus 18 over 5 to the 2/3 power. And 6 is the same thing as 30 over 5. That's going to be 12/5 to the 2/3 power. I can't take cube roots of that So this, I'm going to use a decimal approximation. And as I recall in my previous exam, I just gave people the decimal approximation to a bunch of values. And I said, if any of these will help you out, you can use them. So there you go. I might just do that if you're one of my students. So quickly, I'm going to compute this. And it is approximately 6.5. There we go. And let's label, actually, you know what? I don't need to label this table with local max, local min, and stuff like that, because I'm going to do that on my number line. So these are just for the points itself. Let's see. Anything else? And I want to repeat what I just said, by the way. If you are one of my students and you're working on an exam and you're not allowed a calculator, but yet I know that certain values are going to occur where you'll need a calculator, I will just say, by the way, here's your function evaluated at 10. I'll give you a table of values, half of which, if not all or most, are not going to be useful. But some of them will be, like h at 18/5 will be in that table. That's roughly 6.5. So, but there also might be other numbers in that table that don't get used. So you don't think that every number is a value. Anyway, just thought I'd mention that. All right. That's the first derivative. Anything else I need to mention there? No. Let's take the second derivative. So second derivative, let's look at our first derivative. So this is going to be a quotient rule on that first derivative. Derivative of the numerator is -5 times the denominator. And let's get that done. Minus the numerator, -5x plus 18, times the derivative of that denominator. That denominator is 3 times 6 minus x to the 1/3. Its derivative would be 1/3 times 3, which is 1, times 6 minus x to the -2/3 power times a -1, because of the chain rule, often forgotten. And in the denominator, you're just going to square that. That's 9 times 6 minus x to the 2/3. That's convenient, right now at least, because it makes us think that we don't have to worry about the sign of the denominator, but you'll find out that we might have to. I'm going to multiply numerator and denominator by 6 minus x to the +2/3 power. In other words, I'm going to add 2/3 to all the powers on 6 minus x. That's a good way to think about that. So this will be a -15 times 6 minus x to the 3/3 power minus, so in other words, plus a -5x plus 18. I add 2/3 to that power, so it's to the 0th power, so it's gone. And downstairs, 9, and I add 2/3 power to the exponent there, so it's 4/3 power. And again, actually, this is kind of nice. That denominator will always be positive. Well, except for at 6, but it'll be positive otherwise. So that's kind of nice. Distributing through in the numerator, let's collect all terms with x. I get +15 of them there, -5 of them there, so I get a +10x. And then the constants, I'll have a -80, and plus 18 is a wait, is that a -90? That's a -90. -90 plus 18 is a -72. All right, over. I just remember grading this problem last semester, and that 72 came up, so that's why I do. All right, so here's the second derivative. I happen to know that the second derivative doesn't exist at 6, just like the previous derivative. By the way, once a derivative doesn't exist, all future derivatives will not exist at that point either. And then let's see, the numerator is 0 at 7.2, or in other words, when x is equal to 72 over 10, but it's 7.2. So I'll just put that in here, 7.2. And that's it. Let's test the second derivative. I'll test it at 0. Remember, the denominator will always be positive, except for at 6. So all I have to really worry about is the numerator. When x is 0, it's negative. So negative, so we have concave down. If you plug in anything between 6 and 7.2, like the number 7, you get 70 minus 72, which is negative, so still concave down. and then plug in any number greater than 7.2, like 8, you'll get 80 minus 72, which is positive. Again, that denominator is always positive, so except for at 6, so I don't have to worry about that. So we've actually only added one number to our table, and again, if you were one of my students, you would have a list of, let's just say 10, 20 numbers or something like that, most of which are not going to be very useful, but some of which can be useful, and here's one of those. So 72 tenths, I would probably write it that way, is approximately equal to, and then I will just plug that into that function. And we get roughly 8.1. So again, big laundry list of values in a table that you're handed, maybe at the beginning of an exam. Oh, here's a whole list of values you can use. And so you might find, and they'd be listed in order, right? From lowest X value to highest X value, so that you're not like hunting around in a random order. So anyhow, all right, let's see. I think we have everything ready to go. I'm going to go ahead and pause the video while I draw out my initial graph, and then we'll start from there. Again, you can see from my graph here, I draw the XY axis down below, and I try to use a ruler for this so that it lines up and I know where 0 is on those number lines for H prime and H double prime above. In fact, I'm going to label this H prime and this H double prime. I'm going to erase that vertical line in a moment, but first I'm going to just go ahead and plot my X values. The X values for H prime and H double prime are 3.6, 6, and 7.2. That'll just let me know kind of the scale I want to choose. So maybe I'll say that the X-axis goes from -10 to 10. So if the X-axis goes from -10 to 10, let me decide on how to kind of label this here. There we go. So each one of these little dashes on my number line will be a distance of 1. Well, let's go ahead and plot 3.6 first for the first derivative. So we'll go up here and plot in here 3.6, which is, I have to actually get on the table here, or on the line to do this properly. 1, 2, 3.6, probably right about there. So let me go ahead and just solid dot that. And then I know at 6, sorry, 2 is the last problem. At 6, this derivative doesn't exist, so I'll use red here and I'll zoom in. 1, 2, 3, 4, 5, 6. So I'm going to put a little dot there and do that. See anything else about my first derivative? No. Second derivative, 6 and 7.2. So let me zoom into my second derivative line. And again, I'll put a red open circle at 6. Oops, there we go. 1, 2, 3, 4, 5, 6. There we go. Boom. 6. Zoom down here. 6. And I want 7.2 as well. So if that was 6, 7 and 2, and I need a blue ink for that. 7.2 is probably right about there. All right, that is pretty much all I need for now. Labeled this as 3.2 or 3.6, I think is what I said, and this is 7.2, and this red ink was at 6. And remember, I need to be very careful. The derivative doesn't exist at 6, nor does the second derivative. So we might have a vertical line, we might have a kink, something like that. Usually the graph will showcase it, but it's important. Now that I've done that, I'm going to go ahead and erase that vertical line. Kind of a critical thing to do there, because if you don't, you might convince yourself that you have other intervals, and you just don't. And let's see, we have that it's increasing. Oh, blue ink here instead of red. I have increasing, and then it's decreasing, and then it's increasing. And I happen to know this is a local max, and this is a local min. Well, let's see, second derivative. We have concave down, concave down, concave up. Okay, so concave down, and concave up. Obviously, this would be an inflection point. And that's it. All right, now I'm going to plot my values. Look at the y values. They go from 0 all the way up to 8.1. So that's how I'm going to scale my axes. I'm going to choose to scale them so that the, maybe I'll use the same scaling Let's see if I have enough room here. So 1, 2, 3, 4, 5, 6, 7, 8. I almost have enough room. I might extend that y-axis slightly just to really showcase the pattern there. So maybe I'll do that right now. There we go. Erase that and that. Okay. There's my y-axis. All right. Let's go ahead and plot some points. The points are 0, 0, and 6, 0. So 0, 0 in green. That's the easy one to do. And 6, 0. Let me go ahead and take my ruler over there. There's 6. I'm lining them up. Right there. 6, 0. And what else do we have going on here? Number data above 3.6, 6.5. 3.6 right there. Actually, I'll have to go over on this side, and I want 6.5. So let me line this up. And I'm going to climb 6.5 pips here. 1, 2, 3, and so on and so forth. 4, 5, 6, and some change. So probably right about here, honestly. Do that. So that's 3.6, comma, roughly 6.5. And finally, the 7.2, comma, 8.1. Well, we know 7. I call it 7.6. It's 7.2. I could see it already. It's supposed to be a 7.2. I apologize. So 7.2. You probably already knew that what I meant there, but sorry about that. And 8.1 is the value. Let me line this up. There we go. 2, 4, 6, 8.1 is probably right about here. And let me change out the ink color as well. And I don't need this ruler anymore. All right. I have everything I need. 7.2, 8.1. 7.2, 8.1. So you can see kind of the flow of how I do things. Now I'm going to go ahead and take a look at it. It's concave down and increasing, starting from the left edge over here. It's concave down and increasing. So I know it looks something like, you don't have to start all the way over here. I'm going to kind of connect into this, the point at the origin. It's concave down and increasing. I hope you would agree that's increasing and it's concave down. I happen, because I'm left-handed, I have to graph from left to or right to left. And also, you're going to erase a few times, so keep an eraser on hand, because it's going to be concave down and increasing all the way up to this point, this local max right here. So at the local maximum, it switches from decreasing, but it's still concave down, so it's going to look like this locally. In fact, that might be a good piece of advice there, is when you have these local max and local mins, it might be a good idea to draw there first. So it goes from increasing to decreasing at that local max, and it's concave down. At that local min at x equals 6, which is down here, it goes from decreasing and concave down to let's see, increasing and concave down. Notice what just happened there. It went from decreasing and concave down to increasing and concave down. Now, I'm probably going to have to erase that a little bit just because I'm just getting a little bit of the behavior there. But to make it connect smoothly, I'll probably have to erase to clean it up. And then at that 7.2, it's an inflection point. It's increasing, but it switches from concave down to concave up. Very hard to see that, but that's what it does. All right. So now I can kind of really get a pretty decent graph. I hope you agree this is increasing and concave down here, but I just have to left-handed graph it from the wrong direction. I'm at a disadvantage being left-handed. All right. And then it switches to concave down and decreasing. It was always concave down, but it's switching to decreasing now. And as I said, I'll probably have to erase my little drawing there because I want to make it nice and smooth and clean. Notice I try not to draw through my numbers. Then it goes concave down and increasing, and I'm gonna, because I'm left-handed, I have to do this. try to be as clean as possible for your professor, because you need to really showcase the concavity. If you're not showcasing the concavity, if your professor cannot see that that's actually concave down, you're likely going to be counted as wrong. And then switches to concave up and increasing. Again, you can see it up above, concave up and increasing. That is an accurate graph of this function. Not bad. And we have the fact that the derivative doesn't exist there because it comes down at a point. Very hard to see with my terrible sloppy graphing there. Boop. And you don't have to actually make the sound though. Okay. It's supposed to be pointy there. All right. Pretty good. Not too terrible.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.